Hello everybody, and we start our consultation before the control work, and now we should discuss some tasks from homeworks from our seminars. Okay, do you have seminar 7? Right, so let's discuss number 6. Okay, so the first question is to solve number 6 from the homework 7. Yeah.
Yeah, I actually had a question on seminar 6.
Right. We may start with seminar 6. What's the question?
Question number 10.
Right. Let's start with homework. So homework 6 and task number 10. Find the general solution of the equation y equals 2xy prime plus y squared times y prime cubed. The general solution of this. Well, so the method is we will introduce the parameter p so that y prime is equal to p. P is the derivative of y, and so let's introduce this, and then we can rewrite our equation in the form y equals 2xp plus y squared times p cubed. Okay, now I'd like to, so what's the second step? So this is the first step, introduce the parameter and rewrite our equation in terms of the parameter. But now we have 3 variables, y, x, and p. What shall we do next? Do you know what shall we do next? Find the differential, differentiate, right? The differential of both parts will be dy equals 2p dx plus 2x dp plus 2y p cubed dy plus 3y squared p squared dp. But now we have dy, dx, and dp. But we need 2 variables, not 3 variables. What shall we do next? So we know that from step number 1, we know that dy over dx is equal to p. So we can replace dy by p dx or dx by dy over p. Now we don't know which way is better, so we need to decide, to choose the correct way. So to write this equation in terms of x and p or in terms of y and p. So we need to replace one of the functions by some so we need to actually we need to solve this equation for x in terms of y or for y in terms of x. What's better? Do you know? So step number 3, we find x, solve for x, of course. So 2xp plus y squared p cubed should be solved for x in terms of y. It's better, of course, because it is linear equation, and so solve for x is more convenient, right? So it will be 2xp equals y minus y squared p cubed, and x equals y over p minus so over 2p minus y squared p squared half. Right? So this is x. And now we can replace, so look at this equation. So this is our equation, differential in terms of differentials. And now I will replace x. I will replace x with that expression, and I will replace. So we will solve in terms of y. I will replace dx by dy over p. So I will choose this. Well, but in order to not to lose some solutions, I don't like to divide by 2p, so maybe it is not correct. Let's do the following. Let's first rewrite this equation. Let's multiply it by p. So multiply both sides by p, and we will get, so it will go to p dy equals 2p squared. Let it be 2p times p dx, right? So p dx is equal to dy. So this will be replaced by dy next. Next, plus 2x dp. I will write 2xp dp, and we can see that 2xp is equal to y minus y squared p cubed. So I will replace this by y minus y cubed, y squared p cubed. Next, plus 2y p to 4 dy. It's okay. Plus 3y squared p cubed dp. Now let's make this replacement, and we will get, after this, we will get the differential equation in terms of y and p, and we will be able to solve it. Let's do this. P dy equals 2p dy plus 2xp is replaced by y minus y squared p cubed dp plus 2y p to 4 dy plus 3y squared p cubed dp. So now we are done. Let's combine similar terms. So the similar terms will be the terms containing dy. We will gather them. So we will move all the terms to the left-hand side, and we will get minus p. So minus, I will move it outside. So minus plus 2y p to 4 dy. So I have collected these three terms. Next, it is equal to, next let's collect the other terms, and we will get y plus 2y squared p cubed dp. Okay. Now, if we compare the left-hand side and the right-hand side, we can notice that they are similar, and we can factorize them. Let it be step number 5. I will rewrite this equation in the form minus p times 1 plus 2y p cubed dy equals y times 1 plus 2y p cubed dp. Okay. And from this equation, we can see the following. So let's rewrite it in the form 1 plus 2y p cubed times minus times, just a moment, y dp plus p dy equals 0. Right. From this equation, we can see that the product of two factors is equal to 0. So this means that we have two cases. The first case when 1 plus 2y p cubed equals 0. And the second one is y dp plus p dy equals 0. Okay. And now we need to solve both cases, right? To solve both equations. From this equation, we have y equals minus 1 over 2p cubed. Okay, and together with this formula, we get we get the first family of solutions, not the family of solution, the first solution, right? So since we know that x equals y over 2p minus y squared p cubed half. If we substitute this formula into the last equation, we will get minus 1 over 4p to 4 minus 1 minus p cubed over 8 p to 6, right? And so, am I right? I hope so. So, just a moment. Squared, cubed. Right. It seems to me that it's correct. Minus 1 over 4 p to 4 minus 1 over 8 p cubed. Right. So this is the solution of the first equation, and let's look at the second one. So the second case, if y dp plus p dy equals 0. Okay. Then we have this is very easy, of course. So we can solve this in terms of but it is exact. The solution is yp equals the constant, right? Because this equation is exact. So yp equals c. So from this we have y equals c over p, or so y equals, just a moment. So y may be equal to 0, right? If y equals 0, then it is also possible, right? Y equals 0 is also a solution. Y equals 0. Just a moment, I will have a look. And this is y equals 0 is one of the solutions of the original equation. The second one, so suppose y equals c over p, right? So just a moment. C over p, then x is equal to minus, so it's this c over 2p squared minus c squared p cubed over 2p squared. It is c over 2p squared minus c squared p half. Right. Y equals 0 is the third solution. And let's discuss what happens if p equals 0. So p may be also equal to 0, right? Let's consider this. P equals 0. Then we have, so if p is 0, then y is 0, right? So we need not consider this case, right? So the answer is we have three series of solutions. So the first solution is y equals 0. The second one, x equals c over 2p squared minus c squared p half. And y equals c over p. So maybe we can solve this. Of course, we might try to solve this in terms of. So I think it's better to solve for p and substitute it here, right? So maybe it's better to solve for p and substitute it here. Just let's do this. Or maybe let's leave it in this way. And the last will be x equals minus 1 over 4 p to 4 minus 1 over 8p cubed. Y equals minus 1 over 2p cubed. Okay. So I will. I will have a look. Right. It is right, and the last, I think.
Ma'am, I think x should be minus p by 2p squared.
Just a moment. In which series? In which family of solutions? This one. In the second solution. Here, right?
X is equal to minus p by 2p squared, and then in the next step you miss the minus. On top.
Right. Here, minus.
Yes.
Right. Thank you for this. And now the last. I will check the last in just a moment. Y is equal to minus 1 over, this one. Next substitute, and this will be not p cubed, so not p cubed, it is p squared. So p squared, and so we have p squared here, and so to the fourth power. It will be to the fourth power. And so we may combine these terms and write this as, just a moment, the common denominator will be 8p to 4. And so minus 2, it will be minus 3, right? Minus 3 over 8p to 4, I think. Am I right or not? I hope so. And so I will improve this. It is minus 3 minus 3 over 8. Just a moment. I will change the chalk. I don't like it. I will take my own chalk. Sorry. Minus 3 over 8 p to 4. Okay, so 3 series of solutions, 3 sets of solutions. Y equals 0. This is the second family, right? And this is the last family of solution, the last solution. So just not the family. Only only the second set is the family of solutions. But these are 2 solutions, right? So that's all. It is complicated, of course. Yeah, it is more difficult than the other tasks from this homework, but maybe it's very useful to be able to solve this, right? It's the most difficult task. Next, let's move to seminar 7 and let's discuss task number 6. It's not so difficult, but it's strange a little bit. I will start with this part of the blackboard. So, homework 7, task number 6. Find a particular solution of the differential equation y2 prime equals 0, which satisfies the initial conditions. Y of 1 equals 2 and y prime of 1 equals negative 1. As usual, we will start. So this is a homogeneous equation. So we will start with the characteristic equation. The characteristic equation is lambda squared equals 0. Right? What is the solution of this characteristic equation? Lambda. So both roots will be equal to 0. So a multiple root. 0 is a multiple root. So the general solution should be represented as e to the power 0, so 1, right? Multiplied by c1 plus c2x. For the multiple root, this is the rule for the multiple root. So this is the same as y equals c1 plus c2x. So this is the general solution of this homogeneous equation. Next, let's use these initial conditions. This is step number 1. Step number 2, use the initial conditions. Y prime is equal to, so y, just a moment, y of 1 is equal to C1 plus C2. It must be equal to 2. And y prime is equal to C2, and y prime of 1 is equal to C2 also, is negative 1. So we need to solve simultaneous equations. C1 plus C2 equals 2, and C2 equals negative 1. And we can see from these equations that so C2 is negative 1 and C1 is equal to 3. It must be equal to 3. And so our particular solutions, this is the answer. The particular solution will be 3 minus x. So this is the answer. Very, very easy. In comparison with this task, it is very easy, but very unusual maybe. Right. Just let's do this. Mm-hmm. Mm-hmm. 8, number 15. Right. Mm-hmm. Just let's do this. It's homework 8 and task number 15. Find the general solution of this equation. Minus 3y prime equals 2e to the power 2x sine x. Well, step number 1. Solve a homogeneous equation equals 0. To solve it, we need to create a characteristic equation. And the solutions will be lambda equals 0 and lambda equals 3. There are two roots. And so the complementary function, so the general solution of the homogeneous equation, will be written as C1 times e to the power 0 plus C2 times e to 3x. This is the same as C1 plus C2 e to 3x. Well, step number 2. Let's find the particular solution, a particular solution. Why particular? We will seek the particular solution in the form. Which form do we need? It should resemble, it must resemble the right-hand part, right? We can see the exponential function times sine x, but by the rule, it must be e to 2x times a sine x plus b cos x. Because if we take the derivative of this function, the derivative will include cos x. So our particular solution should be should have the form, this form, a sine x plus b cos x. So ax multiplied by x, you mean? Plus, so where to add this? Before the brackets, so, or, well, you can, right. come here and show me the.
So
What shall we do?
I was asking if we put another constant.
Another constant. Okay, so we needn't do this.
But
right?
we'll still get the correct answer, right?
It will be no, so we will not be. So C will be equal to 0. So we needn't do this. So the rule, the general rule is the following. The general rule for the form of the particular solution is the following. If we have, so suppose the right-hand part has the following form: e to the power ax times some polynomial Pn of x multiplied by cos x plus qm of x times sine x. So this is the general form, the most general form of the right-hand side. Maybe we may have some linear combination of the expressions of this form, but let's consider this case. So e to the power not x but bx, sorry, bx, and bx here, right? Bx. Generally, the right-hand part has this form. Then, so where Pn of x and Qm of x are polynomials of degree n and m, respectively. So the degree of Pn is equal to n, right? And the degree of Qm is equal to m. So our goal is to find the form of a particular solution. So then y particular should be found in the form e to the power ax. Next, we should find the maximum degree from this m or n. So let it be, call it maybe t, the maximum of two integer numbers, m and n. Then it will be some polynomial of degree t multiplied by cos bx plus, let it be polynomial, let's call it s of degree t times sine bx. So this is the form for the particular solution, if there is no resonance. So next we will discuss the case of resonance. The resonance means that, so in this case we can formulate this as follows. We have a resonance if a plus ib is a root of the characteristic polynomial of our homogeneous equation, right? If this is a root, then we have a resonance. Or, in other words, if the right-hand part of our equation resembles the YC, right? But in our case, we have e to 0 and e to 3x, but here we have 2x plus 1. So the solution, the complex number will be 2, so 2 plus I, but this is a not root of the characteristic polynomial. So for our case, this rule works well, right? So let's use it. And so we need not add something c and some polynomial inside the brackets, right? If we consider, if we compare our case with this general case, we can see that we need not add something, right, to our particular solution. So it's enough. Then, so if yp is this, let's differentiate it and substitute into the original equation. Let's find the derivatives. Yp prime will be 2e to 2x times a sine x plus b cos x plus e to 2x times a cos x minus b sine x. Okay, and if we collect terms, we will get 2a minus b times sine x plus a plus 2b cos x. And then we need to know y2 primes p. It will be e to 2x times, if we multiply this by 2 and subtract this, we will get, just a moment, 4a minus 2b minus a minus 2b times sine x, right, multiplied by 2 and subtract the derivative of cos, and plus 2a plus 4b and add 2a minus b times cos x. Right? So let's compute this. It will be 3a minus 4b, and this is 4a plus 3b. Then let's substitute the obtained formulas into the original equation. So let it be step number 3. Step 3, we need to substitute y2 primes. It will be e to 2x times 3a minus 4b sine x plus 4a plus 3b times cos x. It's y double prime, and subtract 3y prime. Subtract 3, these formulas, minus 3 e to 2x times 2a minus b sine x plus a plus 2b cos x. And this must be equal to what? 2 e to 2x sine x. Correct. Next, we can divide by e to 2x because it is never 0. And equate similar terms, equate the coefficients at similar functions, right? These functions. So for sine x, we have the following: 3a minus 4b, next minus 3 multiplied by 2a minus b equals 2. And for cos x, we have 4a plus 3b minus 3 a plus 2b equals 0. And now we need to solve this system of linear equations. We can rewrite it in the form minus 3a minus b equals 2, and minus 3a, not minus 3, just a minus 3b equals 0. So from the last equation we have a equals 3b, and we may substitute it into the first equation, and we will have minus 9b minus b equals 2, from which b is equal to minus 1/5. Is it correct or not? Just a moment, I will check. I have the answers. So, right. Just a moment. So it's number 15. Right, so it's correct. And a equals minus 3/5. Right, minus 3/5. Okay, and now we have a particular solution. Yp equals e to 2x times a sine x. So minus 3/5 sine x minus 1/5 cos x. And then we can write the answer. Y equals y complement plus y particular. So yc is c1 plus c2 e to 3x minus 1/5 e to 2x times 3 sine x plus cos x. So this is the answer. Okay. So it's number 8. Right now, and now I'd like to solve. Just a moment, I will have a look. So 9th question 18. Right. The method of variation of parameter, yeah. So I'd like to consider, so concerning this topic, linear equation with constant coefficients and with the with this form of the right-hand side. So let's solve one question with a resonance. So maybe it's also important. Let's consider the problem with a resonance and with complex roots. So it's, I think it is important. Complex roots and the resonance. So for example, so it is not from the homework, so this is just an example. Y2 primes plus y equals minus 2 sine x minus 4 cos x. No, it's not from seminar. I think it's just some example. Right. So let's solve it. Step number 1, solve a homogeneous equation equals 0. What is the characteristic equation? It is lambda squared plus lambda raised to the 0 power, right? So plus 1 equals 0. So we have complex roots. Lambda equals 1 equals I and lambda equals negative I. So 2 complex roots. So Mohanad sent to me the solutions in the form. So he wrote, then yc equals c1 e to the power ix plus c2 e to the power negative ix. Maybe it's correct in some sense, but I want real solutions, not complex solutions. So please, instead of this, you should write yc equals c1 cos x, right, plus c2 sine x, a real solution of this differential equation, not complex solution, right? So this is y complement. Right. Next, step number 2, we need to write the formula for the trial solution for y particular. So looking at this right-hand part and comparing our right-hand part with the given sample y particular, right, for y particular. So we want to write the following. It is the polynomial of degree 0, so it must be a times sine x plus b times cos x, right? But if we compare this with our y complement, we can see that we have the same functions, right? So this is the same as y complement, so this means a resonance. The coincidence of so as I formulated, given a and b, we can form the complex number a plus ib, right? Given a and b, we can form the complex number a plus ib, and if this complex number is a root of the characteristic equation, then we have a resonance. And in this case, the corresponding complex number will be I, right? Lambda equals I, and this is the same as the I or negative I, and so this is the same as the root of the characteristic equation. So what shall we do if we have the resonance in this case? What shall we do? What must we do? Multiply by x. Multiply by x. We have the coincidence of degree 1, just one coincidence, right? We need to multiply by x raised to the power k, where k is the least power, such that the form of y particular is not the same as y complement. So in our case, the degree of 1 is enough, because we have no terms with x times sine x or x times cos x, so it's enough, right? And now we need to find the derivatives of this and substitute them into our equation, right? So y particular prime will be a cos x minus b sine x times x plus a sine x plus b cos x. And y2 primes will be, so if we differentiate this twice, we will get minus a sine x minus b cos x times x, and plus 2a cos x minus 2b sine x. Next, let's substitute yp2 primes and yp into our equation. I will use this space. Y2 primes plus yp equals minus ax sine x minus bx cos x plus 2a cos x minus 2b sine x, and this must be equal to so plus y, just a moment, plus y. Y is ax sine x plus bx cos x, and this must be equal to minus 2 sine x minus 4 cos x. just combine the terms. So we can see that we have similar terms and we may cancel them out. So we're left with, and we can divide by 2, and we're left with the following. A cos x minus b sin x equals minus sin x minus 2 cos x. I hope it's correct. Right. So A is equal to -2. So we should equate this, and B is equal to 1. So y particular will be equal to cos x minus 2 sin x times x. And the answer will be y equals y complement plus y particular. It is equal to c1 cos x plus c2 sin x plus x times cos x minus 2 sin x. So this is the answer. Okay, and now it's time for seminar 9 and task 18. Solve the differential equation by the method of variation of parameters. Y2 primes plus y equals quad x by the method of Is it okay, right? So this by the method of variation of parameters. So the idea is, first we need to solve the homogeneous equation with constant coefficients. So it will be the characteristic equation is lambda squared plus 1 equals 0. And so lambda equals plus or minus I. And then YC have the following form. It is C1 cos x plus C2 sin x. Right, so this is the first step. This is the simplest part, the simplest part. Step number two. Now the variation of parameters. You can see that we have two constants, C1 and C2. If our equation if our equation were homogeneous, we would have two constants. But now, since it is non-homogeneous, we should think of these constants as functions depending on x, actually, right? So we will look for the solution. We will look for the particular. Let's find the particular solution of this equation in the form u1 times cos x. U1 is a function of x. To emphasize this, I will write this u1 of x times cos x plus u2 of x times sin x. Now, u1 and u2 are not constants, but they are functions. And next we need to find the derivatives and substitute them into our equation. So we can maybe save time and use the result obtained in the lecture, but we may differentiate if we want. In this case, it's not difficult, and so we may try to find the second derivative of up and substitute them into our equation, right? Let's do this. So we need to know yp prime. It is equal to u1 prime cos x plus u1 cos x, u1 minus u1 sin x plus u2 prime sin x plus u2 cos x. And y2 primes p will be u1 2 primes cos x minus let it be right let it be minus if we multiply we will get minus sin x, and let it be minus u1 prime sin x minus 2 multiplied by 2, right? Because if we differentiate the second term, we will get this, right? And minus u1 cos x. Next, plus u2 2 primes sin x plus 2 u2 prime cos x and plus and minus u2 sin x. Okay, well, and next we will collect, so we will add, find the sum of, so this is step number 3 maybe, yp 2 primes plus yp. Let's find the sum of these two functions. We will get, so u2 sin x will and minus u2 sin x will be cancelled out, and u1 cos x will be cancelled out with this term. So the sum of up 2 prime double prime plus up will be u1 double prime cos x plus u2 double prime, so double prime sin x minus 2 u1 prime sin x minus u2 prime cos x. Well, and now we will rewrite this as the derivative. We will do the following. So we have just combined, but we want to rewrite this as the derivative. y1 prime. In just a moment, it will be. Right, so this is equal to okay, and plus u1 prime, just a moment, cos x minus so plus u just a moment, this one, and if we differentiate this, we will get minus sine and minus u1 no it will be I will rewrite it in this form, so minus u1 prime sine x plus u2 prime cos x equals cot x. Right, so I have just rewritten the first row in this form. If we take the derivatives, the derivative of this expression, what is that derivative? The derivative of this will give us u1 2 primes cos x plus u2 2 primes sine x. Right? This is just the explanation. So this expression is equal to this minus u1 prime sine x and plus u2 prime cos x. And if we compare the second term with this, if we add this and this, we will get this, right? So this is the most maybe the most difficult step to rewrite this expression as the derivative and some expression, right? And it is equal to cot x. So it is not difficult to memorize. After I finish this, I will I will teach you how to memorize memorize this. Next, you can see that right, if we try to solve the following equation, just a moment, if we equate the first term to 0 and this to cot x, we will manage to solve our let's try to solve this linear system. If we solve this linear system, this is a linear system in two variables, y1 prime and y2 so u1 prime and u2 prime. There are two variables. These are variables, and if we solve this linear system in terms of u1 prime and u2 prime, we will get the derivatives of our functions. Now we are looking for two unknown functions, u1 of x and u2 of x. This is the way to solve this. But you need not do these steps each time. You can memorize the following. So the rule is, you may write this linear system immediately from this formula. So the rule is, you multiply u1 prime by cos x, right, u2 prime by sine x, and equate them to 0. Okay, so the general rule is the following. Suppose y1 and y2 are two linearly independent solutions of a homogeneous equation. in our case, they are cos x and sin x. They are two linearly independent solutions of our second order homogeneous equation, right? General rule will be the following. So are two solutions. Then we are looking for y particular in the form u1 times y1 plus u2 times y2. And we can write the corresponding linear system immediately from this form. The linear system will be u1 prime times y1 plus u2 prime times u2. This should be equal to 0. And the second equation is u1 prime times the derivative of y1 plus u2 prime times the derivative of u2 equals q of x divided by the constant term. So I mean, if we have a2 y2 primes plus a1 y prime plus y equals q of x, then it will be q of x divided by a2. I have described how to obtain this linear system, but you can memorize this linear system. It's not difficult to memorize. Just take the derivatives of u1 and u2 and form the first equation, right? And then take the derivatives of u1 prime and u2 prime and form the second equation. And by a2, by this coefficient, right? By a2, q of x divided by a2. So this rule was proved in the preceding lecture. It is recorded. You may watch this lecture again, and this linear system was obtained in general case, right? But our problem is the particular case of this general rule. And it is not difficult to memorize this due to the following reason. What is the determinant of this linear system? The determinant of the coefficient matrix of this system. It is Wronskian, right? It is the Wronskian of the functions y1 and y2. So the determinant delta is equal to the Wronskian of y1, y2. The determinant of the following matrix y1 prime, y2 prime, right? And look at the coefficient matrix. It is just this matrix, and the determinant of this matrix is the Wronskian, since we are assumed that y1 and y2 are two linearly independent solutions of a homogeneous equation. Then the Wronskian is never 0 in this case. And we can divide by the Wronskian to find the solutions of this system using the Kramer's rule, right? So after this, let's return to our task. We have this linear system, and we will our goal is to find the formulas for the derivatives of our functions u1 prime and u2 prime using the Kramer's rule. We will use the Kramer's rule, and we will compute the Wronskian in our case. The Wronskian will be cos x sin x minus sin x cos x. It is 1. Very simple. So the Wronskian is 1. And then for the Kramer's rule, we need delta 1. We need to know delta 1. We should replace the first column by the column of constant terms. It will be minus, right, minus cos x. minus cos x. And delta 2 will be cos x minus sin x 0 cot x. It will be, so multiply cos squared over sin x. So since the Wronskian is 1, then delta 1 is equal to u1 prime, and delta 2 is equal to u2 prime. Right, and now we need to integrate this, right? Now we must integrate. Just u1 prime is the integral of cos x dx. It is sin x. We're looking for a particular solution, and so we may not add the constant of integration. And u2, so u2. And u2 will be the integral of cos squared x over sin x dx. It is 1 minus sin squared x. So is it right, or maybe so I know how to solve, but I'm not sure that I'm not mistaken. So not log, right. So it's not difficult, of course. Right, it is dx over sin x. It can be rewritten as so if we multiply by sine, it will be minus d cos x over 1 cos, so sine squared 1 minus cos squared x minus sin x dx. Right. It is 1/2 log okay. I think it's this. u2.
U1 prime minus sin x, because it's integral minus cos x.
Sorry, where?
U1 prime. Yes.
The integral of cos x is sin x, not minus. Minus cos x. We have minus cos x. Minus, and so minus sin x. Thank you. So this is correct. And the final answer. So y particular first. Y particular will be, we must multiply u1 by cos x. So minus sin x cos x. It is minus 1/2 sin 2x. Right? And that plus, so they are cancelled out, plus, so we need not do this because we have the following. So cos x sin x plus 1/2 sin x log cos x minus 1 cos x plus 1. And so these are cancelled out, and so this is a particular solution, if I'm not mistaken. And the answer y equals, so first y complement c1 cos x plus c2 sin x plus 1/2 sin x log cos x minus 1 cos x plus 1. Okay. Hello. Just a moment. I will compare. I think. I hope it's correct. I don't know exactly. I hope it's correct. Right. Okay, I think it's time to take a break and start the control work next.